In the second part of this lecture, we'll be taking a closer look at carbon cycling in the ocean. And as usual, I'll leave you to read through the learning objectives for this part of the lecture. Carbon occurs in a number of pools and takes a number of forms in the ocean. These include the inorganic and organic carbon pools, and the dissolved and particulate forms in each of these pools. So dissolved inorganic carbon, or DIC, includes the dissolved inorganic carbon species CO2, carbonic acid, bicarbonate ion, and the carbonate ion. The particulate inorganic carbon form is effectively calcium carbonate shells in the ocean produced by plankton and zooplankton. And then we have the dissolved organic carbon pool, which is made up of organic carbon compounds that are dissolved. And then we have the particulate organic carbon, which is the zooplankton, phytoplankton, other organisms, and the dead equivalents of all of those. And we can combine some of these things, like the particulate organic carbon plus the dissolved organic carbon equals the total organic carbon. So these pools and forms of carbon are linked through the photosynthesis and respiration of organic matter and organic compounds in the ocean. And we've already taken a look at the biological carbon pump, where we have photosynthesis in the surface ocean producing phytoplankton, which sink. That organic carbon is exported into the deep ocean, where it's broken down and degraded, respired back into its dissolved nutrient and CO2 original forms, and then upwelling brings those dissolved nutrients and CO2 back to the surface ocean, where photosynthesis is then able to use those nutrients and dissolve carbon dioxide again, converting them back into organic matter. So that's largely organic matter cycling, but there's also the inorganic carbon cycling in the ocean. And so that includes the exchange of CO2 between the atmosphere and the surface ocean, and the reactions of that CO2 with water producing carbonic acid, which then dissociates to bicarbonate ions and hydrogen ions. And the calcium carbonate shells produced by phytoplankton and zooplankton use calcium ions, dissolved calcium ions and carbonate ions in seawater, combine those to produce the calcium carbonate shells. So a closer look now at the ocean biological carbon pump. This pump is used to describe the conversion of CO2 to organic matter in the surface ocean, followed by the sinking and then reconversion of that organic matter back to its dissolved carbon dioxide and other nutrient components. So that's the sinking of that organic matter into the deep ocean and then the return by upwelling. It's called a pump because this indicates the CO2 is being pushed up a gradient from the low concentrations of CO2 that occur in the surface ocean toward higher concentrations of CO2 in the deep ocean. Okay, a closer look now at our different pools of carbon in the ocean. So considering the organic carbon pools, we have the particulate pool, and so that includes phytoplankton like diatoms and dinoflagellates, and also zooplankton. It also includes dead phytoplankton and zooplankton and other organic material like fecal pellets from salps and fish and all the other organisms that are consuming organic matter in the surface ocean. These fecal pellets can sink very rapidly into the deeper ocean. A lot of organic matter aggregates into sticky, gooey bits called marine snow that have settled through the ocean at faster speed than the individual particles otherwise would. And then there's the dissolved pool, and the dissolved pool of organic carbon compounds is simply immense and very diverse in its nature. And we're just showing a couple here, chlorophyll A and vitamin B12, but there are many, many of these organic compounds in the dissolved pool. Just an interesting little aside, when we have a look at that dissolved organic carbon pool, so these are all the dissolved organic carbon molecules, and we look at their distribution in the ocean, you can see them going from relatively high concentrations in the surface ocean, and then as we follow the thermohaline circulation around the ocean, so from the top of the North Atlantic here, high latitude, down to the bottom of the ocean and circulating around, then down around Antarctica, and then out in and across the bottom of the Pacific, you can see those concentrations of dissolved organic compounds also break down. So the bacteria aren't just breaking down particles of organic matter, but they're also consuming these dissolved compounds and oxidizing those compounds to release energy so that the bacteria can grow. Moving over to the inorganic carbon pool, these are some of the components. So we have planktic foraminifera that produce these tiny calcium carbonate shells. They're roughly a millimetre or so in diameter. We have the pteropods, which produce these aragonite, also calcium carbonate shells. And these are the free-swimming snails. Coccolithophores, which are very tiny. So this is only 2 microns across, and you can only see these with an electron microscope. And these are, again, calcium carbonate, tiny little shells. And these occur in immense blooms, such as the one shown here off the east coast of New Zealand, that is several hundred kilometres across. So this is seen from space, and this is a giant coccolith bloom made up of these tiny little organisms. And then there are the inorganic dissolved carbon compounds. So that's dissolved CO2 gas, carbonic acid, bicarbonate ions, and carbonate ions. And we can also add coral reefs in here because corals are also extracting calcium and carbonate ions out of seawater and producing calcium carbonate. Taking a closer look at carbon dioxide and oxygen profiles through the ocean. So this is trying to understand that biological pump a little bit more deeply. So the production of organic matter in the surface ocean and its respiration and degradation as it sinks into the deep ocean. So here we have our photosynthesis reaction. Of course, this is the simplified reaction. This is the partial pressure of carbon dioxide in the atmosphere, and these are the measurements in the underlying water going down to 5 kilometres depth. At the surface, CO2 doesn't really get depleted by phytoplankton growth, and that is because there's exchange of CO2 between the atmosphere and the surface ocean, such that the CO2 concentration is maintained fairly close to the partial pressure at which in the atmosphere. However, the CO2 increases significantly as we move into the thermocline, where there is a lot of respiration of this sinking organic matter, which is being reacted with oxygen and reconverted back to CO2. So that's driving this increase in carbon dioxide here. And at the same time, we can see the oxygen is also in the surface ocean is kept close to a particular value by exchange with oxygen in the atmosphere. And as we move deeper into the ocean, the oxygen is consumed by the respiration reaction here that's also producing the CO2. So the oxygen is being consumed and depleted very rapidly in the upper part of the thermocline here. And then these reactions continue down through the ocean, but this water down here is coming from a different source that has a higher oxygen content to begin with, because the water here is sourced from the poles, where the lower temperatures result in a higher oxygen concentration. So just taking another look at that oxygen minimum zone in the central equatorial Pacific. So here it is again, and that's just showing the extent of this bacterial degradation of organic matter that's consuming all of this oxygen in the upper part of the thermocline. And if we then follow the end part of the thermohaline circulation from south to north in the Pacific, you'll notice that the oxygen concentration decreases as we move along that pathway up into the North Pacific. So there's continuing bacterial respiration of organic matter in these waters as we move along that pathway. So the oxygen becomes progressively depleted as the water moves along that pathway. There's this very large low oxygen zone in the North Pacific that comes up to very close to the surface. And just returning to the gas solubilities in seawater. So at 1 atmosphere pressure, the surface of the ocean, where gases can exchange between the surface ocean and the atmosphere, the solubility of a particular gas into the ocean is strongly dependent on temperature. And you can see that for all three of these gases, CO2, nitrogen, and oxygen, the solubility decreases significantly from low temperatures near 0 degrees through to temperatures around here, which are about the maximum in the ocean, around about 30 degrees. So we've got an almost threefold decrease here. And for these other gases, the decrease is about twofold. So the important take-home point here is these gases are more soluble, so you can dissolve more of them in colder surface waters at high latitude. And the change in those solubilities of the gases with temperature explains, in part, what we see in terms of the air-sea fluxes of CO2 between the surface ocean and the atmosphere. So remembering our gyre circulation around here, as this warm water moves towards the poles in the surface ocean, the East Australian current, for example, coming down here, begins absorbing significant amounts of CO2 as it moves south and cools down. Likewise, as this other water moves further north and warms up, this colder water, it starts to release CO2 back to the atmosphere, and this is enhanced by the fact that this area is an upwelling region, and it's bringing very cold CO2-rich water from deeper in the ocean that's accumulated a lot of respired CO2 from bacterial action, and this is then released back to the atmosphere. And you can see quite clearly the patterns that we have with the ocean gyres in all of the ocean basins, and the upwelling regions show up very markedly where that high CO2 colder water is brought to the surface.